Today, we're diving into something really fundamental. It's some fascinating new research from DeepSeek that basically rethinks the very foundation of how we build deep learning models.
You know, for the longest time, the AI race has been all about scale, right? More data, bigger computers. But what if the next huge leap forward doesn't come from just making things bigger? What if it's not about the size of the brain, but the quality of its internal wiring?
So, to really get why this new idea is such a big deal, we have to go back and talk about the unsung hero of modern AI. It's a really simple but totally brilliant idea that has been the engine behind almost every major model for the past decade. It's called the residual connection, and the easiest way to think about it is as an information highway. So in a deep neural network, every layer is processing information, right? The residual connection creates this express lane that takes the original input and just adds it directly to the layer's output. The result is you get the newly processed information plus the original, which helps keep the signal incredibly clear. So why was this simple trick such a game changer? Well, when it was introduced back in 2016, it was the key that unlocked our ability to build ultra-deep networks. By giving the signal this direct path, it pretty much solved the infamous vanishing gradient problem, which meant learning could actually flow through hundreds of layers without fizzling out. And believe it or not, this decade-old design has been the stable foundation for, well, everything.
But here's the thing. As we keep pushing our models deeper and deeper, we're starting to see some cracks in that old foundation. That information highway, when you stretch it out over 1,000 layers, it starts to get noisy. Now, the technical term for this problem is rank collapse or residual accumulation. But honestly, the best way to picture it is just a massive game of telephone. After 1,000 layers of adding a little bit of new information, that original clean signal just gets buried in noise. The message gets lost, and the model's internal ideas start becoming kind of bland and redundant.
Okay, so people have tried to fix this. An early attempt came from ByteDance with something they called hyperconnections. The idea was pretty cool. Let's widen that single highway into a multi-lane superhighway to give the model more flexibility. The problem? There were no rules on this highway. The mixing of information was totally unconstrained, and it led to signal chaos. The model would just become wildly unstable and impossible to train.
And this is where DeepSeek comes in. They looked at this instability problem and came up with a fix that is just so elegant. They've effectively rewired the transformer from the ground up. They call it MAC, which stands for Manifold Constrained Hyperconnections. The core idea is genius, really. They said, let's keep that powerful multi-lane highway from hyperconnections, but let's add some very strict mathematical guardrails. And what you get is the best of both worlds, all that expressive power, but with a rock-solid stability you need to actually train these massive models.
And you know what's crazy? The rules for these guardrails are super simple. Rule 1, all the weights that mix the signals have to be positive. Rule 2, all the weights in every row and every column have to add up to exactly 1. By enforcing these two rules, which they do with a classic algorithm called Sinkhorn-Knopp, they create something called a doubly stochastic matrix. And that's the magic trick. It mathematically guarantees that the total amount of signal going in is the exact same as the total signal coming out. It can't explode, and it can't vanish.
This table just lays it all out perfectly. Your standard residual connection, super stable but not very flexible. Hyperconnections, very flexible, but they just fall apart at scale. And then there's DeepSeek's MHC, hitting that perfect sweet spot. High flexibility and high stability. It's the architecture that gets to have its cake and eat it too.
And really, this quote from the researchers just nails it. They say MHC keeps all the expressive power of hyperconnections while bringing back that identity guarantee, that stable core signal that made deep learning possible to begin with.
Okay, this is huge for language models for sure. But the real question is this a one-trick pony or is it something bigger? To find out if this was a truly universal principle, the researchers took it for a spin in a completely different area of AI.
They applied the exact same MHC idea to something called graph neural networks, or GNNs. And guess what? GNNs have their own version of the game of telephone problem. It's called oversmoothing. As you make the network deeper, the information from all the different points on the graph just kind of blends together until everything looks the same and all the unique, valuable information is lost.
The results here are just staggering. I mean, look at this chart. They trained a GNN that was 128 layers deep, a depth that is usually totally unusable. The standard model, its accuracy completely collapses down to about 21%, which is basically just guessing.
But the GNN with the new MHC wiring, it's sitting there with over 74% accuracy.
That is an absolute accuracy jump of almost 53 percentage points. Let that sink in. We are not talking about a little tweak here. This is the difference between a model that completely fails and one that works incredibly well. This proves the principle is truly fundamental.
So what's the big picture here? What does this all mean? Well, we could be looking at the next major architectural leap for all of AI, built on a foundation that's just way stronger and more stable than what we had before.
The main takeaway is pretty clear, right? While making things bigger will always be part of the story, this research proves that innovating on the fundamental wiring, the architecture itself, is just as critical, if not more so. Better wiring lets us train more stable models, which lets us build deeper, more capable, and ultimately smarter AI.
And that just leaves us with this one huge question. For years, the depth of our models has been a serious bottleneck. Now that we have a technique that seems to unlock our ability to go deeper and do it reliably, what does that open up? What new frontiers can we explore? What kinds of complex problems that were totally out of reach before can AI finally start to solve?